in a more rigorous definition of what quasiparticles are and when they exist can be obtained by looking at the many-body excitation spectrum of a quantum system. So if your excitation spectrum has a structure that it can be written in terms of a low-order polynomial in occupation numbers n alpha, then one would say that such a system has quasiparticles, and n alpha is the occupation number of a quasiparticle state denoted by alpha. And then if you look at single particle spectral function in this basis denoted by alpha, if you have well-defined quasiparticles, you'll have a peak at the excitation energy of the quasiparticle, and the width of the quasiparticle peak will be much smaller than the excitation itself. So it's a well-defined quantity that lives at a particular energy. Okay. Yeah, so this quasiparticle basis alpha can also be quite non-trivial. A simple example would be just a disordered metal. So you just have a non-interacting band with a random potential in it. And you say if you looked at the Green's function in the momentum basis of the band, you get a decay rate of your quasiparticles that is pretty large. It actually doesn't go to zero as the excitation energy goes to zero. So you might think that quasiparticles are not well defined, but it's a non-interacting system, and you can go to the exact eigenstate basis, and there you have a Green's function that corresponds to a sharp spectral function. So quasiparticles are well defined. And in that, another way of looking at it is that this potential causes only elastic scattering of your band fermions, and then single particle states at different energies are not mixed, and you just rotate your basis of quasiparticles. However, if you have interactions, you can get inelastic scattering, which mixes states at different energies, and then one can start to degrade quasiparticles. So, like in another system where you have inelastic scattering, but it still has well-defined quasiparticles, is the usual Landau Fermi liquid, in which you have density interactions, which in terms of a Hubbard-Stratonovich transformation can be written as being mediated by a boson that is screened, and therefore it's gapped and mediate short-range interactions. And that boson will definitely mediate inelastic scattering processes. So if you have this kind of scattering process, the in and out fermions here don't necessarily have the same energy, so it's inelastic. However, all your in and out states lie near the Fermi surface, and if you compute the scattering rate using Fermi's golden rule, because of the constraint that everything has to be near the Fermi surface, one gets a scattering rate that is proportional to the square of the energy of the excitations. And because that square of the energy is much smaller than the energy itself, the individual excitations remain well-defined quasiparticles. But the scattering is inelastic in nature, and it has an energy-dependent rate, unlike the elastic scattering from a disorder potential, which had an energy-independent rate. Okay. So a strange metal will be something quite different. So these strange metals they're also metallic and they have a finite charge density and they're compressible just like a Fermi liquid, but they have some very different properties. So these things are usually found in two-dimensional or quasi-two-dimensional layered materials. They have electrical resistivity that has a linear in temperature dependence, and they're usually proximate to quantum critical points in between phase transitions between different quantum phases. So some of the experimental signatures of the strange metals are one is they have the resistivity that varies linearly in temperature down to very low temperatures. So there are systems like the cuprate superconductors in which if you suppress superconductivity by applying a magnetic field, you find that the resistivity goes linearly down at very low temperatures. Also seen in heavy fermion materials like this one, where they actually can see this behavior down to extremely low temperatures. And more recent interesting cases in this magic angle twisted bilayer graphene system, where the T-linear resistivity is again seen down to extremely low temperatures. So this resistivity is also relatively small in a strange metal, that it's smaller than the quantum of resistance in two spatial dimensions. And that one can also have regimes in which there's T-linear resistivity, but it's much larger than the quantum of resistance, and those are different. Those are called bad metals, and these bad metals will not be a subject of this talk. So other experimental signatures of strange metals that as I said earlier, they occur in proximity to quantum critical points in various correlated electron materials. And one way to tune between different phases in a correlated electron material going through a quantum critical point is by changing the doping of dopant atoms in that material. So that's what one can do in like a cuprate or a heavy fermion situation. So there's one usually sees that as you vary the doping and go through this critical transition region, the specific heat takes a peak, and then also the temperature dependence of the specific heat is that it's C over T scales as log T, so C is T log T at low temperatures. And this is seen in like cuprates and heavy fermion materials, and also in pnictides in many different places. So this is the enhanced specific heat, that C over T diverges as T goes to 0, which implies that there are a lot of soft excitations at low energy. In a Fermi liquid, one would just have C over T going to a constant as T goes to 0 and not diverging. So there's something more to the system than just the excitation structure of a Fermi liquid. We call this large specific heat. And there are now even more experimental signatures which actually show that like electron-electron scattering going on in strange metal is inelastic. So one way in which that can be shown is to measure the frequency dependence of your electron-electron scattering rate. That's 1 over tau. And one can do that by, say, measuring the optical conductivity. So in, like, say, this particular experiment on cuprates, the optical conductivity fits this particular form, and this 1 over tau, which is the y-axis here, is 1 over tau, which is your scattering rate, is strongly frequency dependent, and it scales as the frequency times some scaling function of omega over t. Strongly frequency dependent scattering rate is a sign of inelasticity, and it's also quite large in magnitude. So especially as you start turning up omega, so certainly large enough that the scattering rate is large enough that you can't define a quasi-particle effectively. And it's also seen in photo emission experiments where it's not a transport measurement of optical conductivity, but rather just a measurement of the single electron spectral function itself. And then again, there's this large omega linear scattering rate. And then there's a very recent and interesting probe into the nature of electron-electron scattering in strange metals, and that is by measuring the short noise in electrical conduction. So in a traditional metal with well-defined quasiparticles at low temperatures, like say gold, because you have this discrete granularity of the charge carriers, they are individual quasiparticles. If one looks at the time-resolved current signal, it's not a continuous stream, but it consists of several closely spaced spikes that are as your discrete electrons arrive at the detector, and one can, so that it's actually a noisy signal that you get if you time resolve it well, and that's precisely that noise in there is called the short noise, and one can quantify the short noise by measuring the power spectrum and determining this quantity called the Fano factor, which is basically proportional to the power spectrum of the short noise. So, in like a metal which has purely elastic scattering at low temperatures, like gold, it gives a particular value of this Fano factor. But so people now have this very nice paper work here. They have done the same experiment on this strange metal that I showed you on the earlier side, this heavy fermion material, and they find that the short noise or the Fano factor is much lower than what you would expect in just a Fermi liquid, a weakly interacting metal with elastic scattering. Instead of like around 0.3, it goes down to 0.15 or so. So in the interpretation of that is that you have a lot of elastic scattering that's mixing quasiparticles and blurring them out across different energies, so you don't have well-defined quasiparticles anymore, and then you don't get this series of resolved spikes. You see something that's more smeared out and continuous in your time resolved current, and that gives you a less noisy signal and lower short noise. So we actually have some theory work on this, which was done with Alex Nikolenko, who is in the audience, where we use models that I will talk about later in this lecture, and actually reproduce this physics and show that it's due to inelastic scattering and lack of quasiparticles. So if you're interested in that, you can take a look at this paper. So what are strange metals not? They're not Fermi liquids. And Fermi liquids have this T-square quasiparticle decay rate, which would also lead to a T-square resistivity, because you would count the quasiparticle decays that also decay current via Ohm-Clap processes, and you can't get a T-linear resistivity out of that. And while electron-phonon scattering can give T-linear resistivity, it only occurs above some temperature scale that is either a Debye temperature scale for gapped local phonons, or if you have acoustic phonons, then it's something called a Bloch-Gruneisen temperature scale that corresponds to the energy a phonon must have to scatter electron from one end of the Fermi surface to another. But these energy scales usually range in like the range of several tens to hundreds of Kelvin, and T-linear resistivity has been shown to persist on much lower scales. And furthermore, like electron-phonon scattering in this high temperature regime where it gives T-linear resistivity is also elastic, and it can't give you an omega linear optical scattering rate, or it can't give you suppressed short noise either. So it like the strange metal behavior can't involve electron phonon scattering at low temperatures. And therefore, it must arise from inelastic electron-electron scattering and strongly degraded quasiparticles. So if we want to start developing theories for strange metals which have very strong inelastic scattering and poorly defined or no quasiparticles, it helps to have a toy model that you can solve exactly in some special case. So the toy model that is a building block for various theories of strange metals is called the Sachdeva-Kitaev or SYK model. So this is a pretty simple model where, say, you have a zero-dimensional atom with many orbitals in it, like these are orbitals on the blue dots here, and there are n orbitals, and you take the limit n being very large. So then you place fermions randomly in this orbital, and then you have this random 4-fermion interaction that moves a pair of fermions from one pair of orbitals to another. And this interaction has all-to-all connectivity across the orbitals and a random complex matrix element GIJKL with zero mean, and it's drawn from a Gaussian distribution with some variance that has a sort of scaling in n. So this just has an interaction term. It doesn't have any quadratic term in Hamiltonian at all. So it leads to purely inelastic scattering. And because of this limit of large n and random coupling, one can write down an exact equation for the fermion self-energy, where you take this vertex and put it on both sides, and because this coupling is random, it restricts the combinations of flavors that can go through these lines. So you have your self-energy that has this expression in terms of the Green's function, and this thing is called a Schwinger-Dyson equation, and you get this exactly in the large n limit. And this Schwinger-Dyson equation can be solved, and what it gives you is that it gives you a Green's function or a spectral function that has this power law behavior. It scales as 1 over square root omega. So there's no Lorentzian structure or no quasi-particle peak in here. You just have something that's spread out over a very large frequency range. And so like this, there's no quasi-particle excitations in this model that you can solve exactly. And another way of getting the Schwinger-Dyson equation is that you can write the partition function of this model in the large n limit in terms of a saddle point, where if you average over this disorder explicitly, which you have to do a replica method for, then one can do that and then integrate out the fermions and write down a saddle point in terms of these bilocal G and sigma fields, which are nothing but your fermion Green's function and the self-energy. And then the saddle point criterion that delta S is 0 with respect to these fields, that gives you the Schwinger-Dyson equation on the previous slide. So, and furthermore, you can also, this is a model that you can just put on a computer and diagonalize, and then what we see in the low energy spectrum is that you have a level spacing that scales are exponentially small in n. So you have many low energy states packed very close to each other as n goes large, and that's incompatible with this kind of polynomial expression of excitation energies in terms of occupation numbers that you would expect from a quasi-particle structure. So this is like a really foolproof demonstration that there are no quasi-particle excitations in this model. Yeah. So there's a certain variant of this SYK model that's useful for everything that I will talk about going forward, and that's the Yukawa SYK model. So instead of writing a random 4 fermion interaction, we can write down a random interaction between fermions and bosons. And this has this Yukawa coupling form psi dagger psi phi, where psi is your fermion and phi is your boson. But this is also in a large n limit, so all your psi's and phi's have a flavor index that goes from 1 to n, and you have this random matrix element GIJL that's also got like a 0 mean and non-zero variance, and that leads to now Schwinger-Dyson equation, which gives you self energies for both your fermions and your bosons, which look like these diagrams. And this has this familiar form of self-consistent Migdal-Eliashberg equations, where you sum all rainbow graphs for your self energy and all the bubble diagrams for your boson polarization. So that that gives you a equation for fermion Green's function that looks like this, and a boson Green's function that looks like that. And this is again just a 0-dimensional atom with many orbitals, so you only have a frequency dependence, and one can again solve these equations via a power law ansatz, and you get the power law with some exponent that depends on like the ratio of number of fermions to bosons, and if it's 1, then that ratio is 1, then you have this particular value of exponent. But the thing to note again is that your spectral function for the fermion and the boson, they're just power laws. They don't have any like Lorentzian or delta function peaks, and there's no sign of quasiparticles. And one can again also study this model by exact diagonalization on a computer, where you can integrate out the boson and solve an effective 4 fermion model with a different coupling structure. But if you do that, then again you get the same properties as the previous plain vanilla SYK model, that it has an exponentially large density of states at low energies, and there are no quasiparticle excitations. Okay, so with these things as building blocks, one can now start to think about like a non-Fermi liquid metal that lives in space, and it's not restricted to a 0-dimensional atom. So the traditional way in which people have tried to write down models of non-Fermi liquids is that you take a band of fermions and it has some chemical potentials would have a Fermi surface, and then you Yukawa couple your fermions to this bosonic field that represents an order parameter going through a quantum critical point. So you have this Fermi surface coupled with quantum critical bosonic order parameter, and this model is proven like you can't solve this thing exactly analytically at all. That people have tried many different kinds of approximations, but this is also this particular structure with this Yukawa coupling means that it's amenable to doing this Yukawa SYK like trick. So one can promote your fermions and bosons to have large n number of flavors per spatial site. So you still keep your k indices and momentum and space index, but you add an additional flavor index to both fermions and bosons that ranges from 1 to n. And then you also take into account the other feature of the Yukawa SYK model, that your coupling G is now upgraded to this random tensor in flavor space, but it's spatially uniform. So you have the same random tensor on each spatial site. And then this does the same thing as it did in the Yukawa SYK model in the sense that it again gives you if you take the large n limit and you get these Migdal-Eliashberg equations for from the large n saddle point that you got even in the zero-dimensional Yukawa SYK model. But this, because it has spatial structure, you also have these dispersion terms in your boson and fermion Green's functions, and that changes the solution. So you get this damping term in your boson self energy, and you get a power law term in your fermion self energy, but the exponents are quite different from what you see in these SYK models. So the self energy of the fermion doesn't depend on momentum, but it depends on frequency, and the frequency dependence is omega to the 2/3. So it's strongly depending on frequency, which indicates inelastic scattering, and it's also large. It's like omega to the 2/3 larger than omega, so it's larger than the excitation energy itself, and therefore there are no well-defined fermion quasiparticles. And the same thing happens to the boson. So like this solution of the Migdal-Eliashberg equations was for this this non-Fermi liquid model was done ages ago, I think all the way back to 1989. But the Migdal-Eliashberg equations were not justified in terms of their applicability. But now we can understand that these Migdal-Eliashberg equations are actually exact for a particular model that has this large n number of flavors per site and the random tensor coupling. So that's very nice, but like a physical system doesn't actually have any large n. So even though this large n can justify Migdal-Eliashberg in large n limit, one still doesn't know if Migdal-Eliashberg is valid when n is small, but we can also make progress towards that by studying the large n model. So again, if you write down the saddle point action in terms of these bilocal Green's function fields that I told you about earlier, the fluctuations about that saddle point can be written in terms of fluctuations of this bilocal field, and that has a propagator of bilocal fields that you can compute. And that propagator is actually gapped, so there's like no unit eigenvalue of this term k here. So that means this quantity in brackets never goes to 0. So there's like these fluctuations are always gapped out, and because fluctuations are gapped, that means that the saddle point is actually relatively stable, even as you start to make n finite instead of large. And therefore, one can hope that the saddle point that gives you Migdal-Eliashberg is even valid at finite n. So people have done comparisons of solution of Migdal-Eliashberg equations to numerics at finite n. So one way to do numerics is there's a sign problem-free quantum Monte Carlo model for this non-Fermi liquids, and the people compute the fermion boson self energies, and then they can compare what they get from the QMC with both the continuum Migdal-Eliashberg theory and lattice discretization of the Migdal-Eliashberg theory, and there's reasonably good agreement with the exact solution for the fermion self energy and also for the boson self energy. So that's another check on Migdal-Eliashberg theory actually having something to say about these models. So armed with that, one can say, okay, that we can solve things in this saddle point formalism and Migdal-Eliashberg, and what does transport look like, and how many of these remarkable transport properties of strange metals can be reproduced by this non-Fermi liquid model with no quasiparticles. And it turns out none, because this model that I just talked about is translationally invariant, and that because translationally invariant, the total momentum is conserved, and you have finite charge density, then you cannot relax current when you have a totally conserved momentum, and therefore your resistivity is zero. You don't in the low energy theory, and not linear in T, and you don't get this linear in omega scattering rate in optical conductivity either. So one needs to, if you want to get these interesting features, one needs to add momentum dissipation to this theory, and at low energies, the only viable way to do that is by adding impurities. Like phonons another way, but phonons don't do anything much at low temperatures. So I mean, impurities definitely exist, like cuprates, for instance, have a lot of disorder, and people have seen things like spin glass antiferromagnets at low doping, and cuprates, which are definitely signs that there's plenty of disorder. And another interesting thing is it only seems to be that that materials which have plenty of disorder produce this strange metal behavior. So like twisted bilayer graphene does, and it has twist angle disorder, but there are also non-twisted, strongly interacting multilayer graphene metals or materials which have almost no disorder, but they still do things like go superconducting at very low temperatures, but they don't actually show any T-linear resistivity anywhere. So that's another indication that disorder could be important. So if we take our non-Fermi liquid metal and we just add spatially random potential disorder to it, so you add a chemical potential here that's random in space, no mean and finite variance. Well, that changes your low energy structure of your Bear-Green's function. You get this constant scattering, elastic scattering rate here, and because that structure changes, then the form of damping of your boson within Ringdahl-Eliashberg changes, and the form of fermion self-energy changes. Now it becomes omega log omega instead of omega to the 2/3. So it still has a pretty large scattering rate, and the quasiparticles are still degraded. One can now ask whether the transport properties are any different. So the first thing is that, well, this disorder leads to an impurity scattering rate that just gives you a constant resistivity as temperature goes to 0. But the inelastic part of the scattering that comes from scattering fermions of these bosons. These bosons are at small q, so this inelastic scattering barely changes your current, like the fermion direction of your fermion momentum doesn't change. This is the usual forward scattering problem, and therefore, because this not affecting the current, this scattering rate actually doesn't represent the current relaxation rate, and therefore it doesn't contribute to the resistivity. So the resistivity at low temperatures is just a constant plus T squared. There's no T-linear term. So we know that disorder is important, so one can ask what else can it affect? It can affect the random potential for the fermion. But one can also have a random fermion boson coupling, so there can be a randomness in the Yukawa coupling, which is equivalent to having a randomness in your boson mass if you just rescale your boson fields. So if we take into account that disorder in the coupling, then one one can again do your Mingdal-Eliashberg, and you have this 1 over q square plus mod omega boson propagator in 2 spatial dimensions. And now we get 2 contributions to the fermion self-energy. One comes from the uniform part of the coupling, the other one comes from the random part. And they both scale as omega log omega, and which means that the imaginary part has the relaxation rate, the linear in frequency for both. However, the thing that has the random interaction allows you to scatter fermions by a large angle, even though the boson might be at small momentum, because you have this additional momentum being imparted by the randomness in the interaction itself. And that would mean that your omega log omega self-energy, or your linear in omega scattering rate that comes from this, now translates into a current relaxation rate, and therefore it contributes to the resistivity. So then one does get linear in T contribution to the resistivity from this, and also in the optical conductivity, one gets a linear in omega optical scattering rate, because this is an inelastic process that's mediated by this interaction. And furthermore, these critical bosons with dynamical exponent 2, they also produce a T log T specific heat in 2 dimensions. So this very simple model now just gives you 3 features of the strange metals that I talked about earlier. And like we also computed short noise properties with this thing, and found pretty good qualitative agreement with what goes on in that experiment, which I mentioned earlier. So this model seems to do very well. So one can ask, it has this little unusual thing, which are disordered interactions, and one can ask, where do they really come from? It's not that hard to get them. So for instance, one can take a Hubbard model style picture and say that there's some disorder in the hopping itself due to irregularities in the placement of the atoms or strain or other things. And in that, since in the Hubbard model, one has this antiferromagnetic J interaction, that's T square over U, a disorder in the hopping T would give you disorder in your antiferromagnetic interaction itself. And that disorder in antiferromagnetic interaction, if you do Hubbard-Stratonovich decoupling, it would become disorder in this Yukawa coupling in this kind of model. So yeah.
Yeah, but I think you need the mean of the Yukawa coupling to be 0, right?
No, the mean is never 0. So the mean is not 0. It's G plus G prime. Yeah. So it all works with non-zero mean. Okay. Any other questions? Okay, fine. All right. So I demonstrated this random coupling mechanism for bosons that live near Q equals 0, but one can also look at bosons that live near finite Q, like in an antiferromagnetic interaction. And so the uniform part of the interaction just affects only some hotspots on the Fermi surface now, which don't contribute much to transport because they're very small regions. But the non-uniform part, this G prime part, that affects everything on the Fermi surface, and it actually doesn't care about this finite wave vector, because G prime is a random combination of all possible wave vectors, so it just shifts it by finite wave vector, which gives you back the same thing itself. So the G prime part of the interaction works in exactly the same way. So like any point on the Fermi surface can scatter to any other point by absorbing a low energy, low Q boson, and one gets this omega linear, T linear scattering rate now all over the Fermi surface instead of just at the hotspots. and you get linear resistivity. And furthermore, this thing can also extend to more exotic systems, like ones which have of the Kondo lattice type with two bands. So in a Kondo lattice model, you have a Kondo coupling between your conduction spins that are small s and some valence spins that are large s. And one can have randomness in this Kondo coupling. So you can write your valence spins in a fractionalized language in terms of spin-ons with this occupancy constraint. And then write your model of this coupling in terms of a Yukawa coupling to a hybridization field, B that's conjugate to F dagger C, and then condensation of B like hybridizes your C and F Fermi surfaces, so it converts your small C Fermi surface to large C plus F Fermi surface without any symmetry breaking. And that was pointed out in this seminal paper many years ago. So there are materials in experiment which actually do this. There's this very nice paper from 2021 which looks at these heavy fermion materials that are like C coin 5 and LA coin 5, where they have a bunch of, they have a valence band and a conduction band, and one has actually has a transition from large to small to large Fermi surface volume by making only a small change in the doping. So it's been measured through like the Hall coefficient, and there's like a large change in the Hall coefficient for only a small change in the doping, and that's been argued to be due to like C plus F hybridization, and there's like no symmetry breaking, like antiferromagnetic density wave order anything detected through this transition. And furthermore, this through the transition, the critical region shows T linear resistivity down to very low T, so it's a strange metal too. And then one can actually understand this, and if we write this down in the fractionalized language, where one has some spatially uniform coupling, but now has a disorder fluctuation about it that just comes from the disorder in the Kondo coupling. So then the spatially uniform coupling doesn't contribute to inelastic scattering for your conduction electrons, because your Fermi surfaces are distinct, and usually when your boson is at small momentum, you cannot, like your interaction will convert your C fermion to an F fermion that's very far from the Fermi surface, and it's off shell, so it doesn't cause any absorption of energy or inelastic scattering. But the disordered part of the interaction doesn't have that problem, because it carries an arbitrary amount of momentum, so it can like scatter you from anywhere on the C to anywhere on the F Fermi surface by soft low Q bosons. So again, like one gets a transport scattering rate of your conduction electrons is dominated by the disordered interaction, and that gives you, again, in two spatial dimensions, it gives you a marginal Fermi liquid and T linear resistivity. And we've done the full calculation in this paper that takes into account contributions of C, F, and B properly, and we still show that in the end we just have a T linear resistivity at the critical point. So this, I've described this mechanism with randomness in the Yukawa coupling that can lead to T linear resistivity in two spatial dimensions. That also seems pretty universal. It works for many different kinds of order parameters. So of late, we have also been working on like trying to do numerical simulations of models with spatially random interactions. So we take this particular version of a model with antiferromagnetic interactions and make the antiferromagnetic interactions spatially random. And this model has a a two-band structure, and because of that, it has no sign problem in quantum Monte Carlo. So we can actually simulate this with determinantal quantum Monte Carlo, which was sort of the model with spatially uniform interaction was studied many years ago, but now we consider it the one with spatially random interactions because that's really the new thing that gives you unusual physics. I mean, you can also do G plus G prime, but we just isolate this with just G prime just to isolate its effects. So we use a different algorithm to do this than the usual determinantal quantum Monte Carlo because we want to reach large system sizes, pretty large system sizes, like 40 by 40 or like 80 by 80 system sizes, so that you're not looking at a system that looks like just one patch of the disorder, like you just have enough sites in the system to like sample across the whole distribution of disorder. So we use a different algorithm that's higher performance and that can handle these system sizes. So that algorithm is called hybrid Monte Carlo. So it's also a determinantal method that you just take this theory and integrate out the fermions, and then you're left with an action that is purely bosonic, and it contains a term that is a fermion determinant that's a function of your bosonic field, and it's sign problem free, so this determinant is a perfect square and it's always positive. But the problem in determinantal Monte Carlo is that computing this determinant is a very expensive procedure, and that limits the kind of system sizes you can do. So instead, what we do is we rewrite this action with this standard identity where phi and phi star are complex scalar fields. So now you have three scalar fields that you can jointly sample over in order to compute this action rather than actually computing the determinant at each step. So it's just a sampling problem. And instead of computing the determinant, one has to compute the inverse of this matrix times some scalar, and that's much easier to do. And this technique is actually standard in the lattice QCD community. It's like not very much used in condensed matter, but it's been used for like more than 30 years in lattice QCD. So there is an additional component to this to like update like phi and var phi fields, where they're updated by evolving them along trajectories with randomly sampled momentum. And in the computationally expensive step, as I said earlier, one has to compute this inverse of this matrix times some var phi, but that can be done with an iterative solver and like a conjugate gradient algorithm, and one can implement that very efficiently on like this GPU hardware that's like in the news for all kinds of machine learning these days. But one can, if you have access to it, one can do quantum Monte Carlo on this efficiently with this algorithm. So we did that. We wrote this, developed this whole big code, and like fed it this G prime models, and we see that they do have a function of a critical tuning parameter. They exhibit continuous phase transition and have a continuous evolution of the susceptibility, and then you can compute your binder equivalent and determine the location of the critical point where curves intersect, and we can do pretty large system sizes. So when we have a pretty large system size, we don't need to average over a very large number of disorder realizations. So like a 10 or few tens are enough, and that's a real advantage. with determinantal QMC, you would probably be able to get to like L12 or 14 in these kind of models, and then you have to average over hundreds or up to 1,000 disorder samples. So we can do all this. We can compute what the boson propagator looks like, and find that detection. Very nicely has this q square plus mod omega scaling at small q and small omega, where omega is much less than the Fermi energy in the system. And so these are various values of the parameter. And so this boson propagator is also what you get by doing Mingdal-Eliash work for the disorder theory. It's not really surprising because they have the property that this large n saddle point is fairly stable. And one can also compute fermion self-energy and extract its frequency dependence. So if we look at the dependence on the fermion self-energy that comes from finite Matsubara frequency bosonic fluctuations, that would be really resolving this frequency dependence that you see here. So if you subtract out this constant part that comes from the thermal fluctuations, then one gets that your self-energy on your Matsubara axis is an order dependence that is roughly constant plus omega, that can be fit to constant plus omega log omega, which is compatible with the marginal Fermi liquid form. This is still at like fairly high temperatures, so we're pushing this to go down to lower temperatures and get a better fit to this log and like more firmly establish this marginal Fermi liquid form. But so far it looks like it's what we're getting is consistent with that. So with that, I reach the conclusion of this talk that strange metals they're metallic compressible systems, but they lack well-defined quasi-particle excitations, and they're dominated by inelastic scattering. And one really has to understand that in order to understand their physics. And techniques based on SYK model and large n limits can properly justify the use of a very well-known Mingdal-Eliash approximation to study strange metals, because it shows that it's a reasonably stable saddle point of an action. And then one needs to have disorder in order to get unusual transport properties, and specifically disorder in electron-electron interactions in order to obtain like the T-linear and omega linear scattering rates that are seen in DC and optical conductivity experiments. And the transport physics is insensitive to the nature of the order parameter. It can be antiferromagnetic, it can be a Kondo lattice model, it can be a Q equals 0 order parameter, and therefore this mechanism can apply across many different materials as long as they're like quasi two-dimensional, which most strange metals are quasi two-dimensional. And then finally, like even though we have this the system with significant amount of disorders, we can remarkably do high quality exact quantum Monte Carlo simulations, and also show that like our theoretical calculations, which are only exactly justifiable in the large n limit, they also work reasonably well at finite n, like comparing with the exact numerics. With that, let's take questions.
Question?
What is the physical origin of the boson you mentioned?
So it corresponds to a fluctuating order parameter in the symmetry breaking transition, for instance, like your antiferromagnetic order parameter, the usual quantum critical boson, like near an ordering transition. Or in the Kondo lattice model, it's what's called a slave boson. It's an emergent field that doesn't break symmetries, but it's still an order parameter that is a hybridization of your conduction electrons with spin-ons.
Also, when you do these finite n simulations,
Yes.
what is the value of n?
What's the value of n? It's only the number of spins and also like the number. It's sign problem free, so you also double the number of bands. It's 4.
Other questions?
Yeah, so
And this relates to the previous question. So the bosonic model incorporates the strange metal behaviors measured up to 1,000 Kelvin. It's a bit hard to imagine a bosonic model would behave same way for such a large temperature range, right?
Right. So this as I said, I'm not focusing on this bad metal region. This is only a low. I'm not focusing on the bad metal region that goes up to 1,000 Kelvin. I'm only being like this model is only meant for like low temperature physics. Right?
Okay. It's a straight line, right?
Well, it's not necessarily a straight line. It's a straight line at some values of the doping, but like at other values there is a kink. So in order to study what happens at high temperatures, one has to take a model like this and crank up the coupling as well as the temperature, and then see what happens to the resistivity at high temperatures, which is an open question, and we're trying to work on that using DMFT and other such methods. But we don't have results yet.
Any other questions? So we have a question from the webinar. Does disorder in the interactions always lead to linear T resistivity? And can one obtain arbitrary scaling laws?
So the T linear resistivity comes from with the disordered interactions comes from being in 2 dimensions, because your boson propagator is 1 over q square, and when you have disorder, you couple to the local bosonic fluctuations. So integral d2q over q square gives this log susceptibility that's ultimately responsible for the marginal Fermi liquid. But in 3 spatial dimensions, you'll have a different local susceptibility. So you'll get a different power, like t to the 3 half in 3 spatial dimensions. So that's one way you can get a different power. But yeah, as long as you're in 2 dimensions, you'll almost always get T-linear resistivity. And most strange metals are actually quasi 2-dimensional at the end of the day.
Yeah, just as a following question. So basically, the string metal is not only strange because of the T-linear, but also because it's kind of Planckian timescale. Can this theory explain why like all the scalar is kind of universal thing?
Yeah, so in the limit of strong coupling, right, one actually gets Planckian dissipation the way the experimentalists define it, because your fermion self-energy controls both your effective mass renormalization as well as the scattering rate. And like the Planckian time is nothing but the scattering ratio of the scattering rate to the effective mass renormalization factor, and the coupling ends up canceling out in that. So you end up with a number that's quite close to kBT over h bar in that case. But yeah, you need to be a strong coupling for that to happen.
Other questions? If not, let's thank the speaker again. And this is the last lecture of the Sound School, and thank you all for coming, and have a safe travel back. Thank you.